hello everyone, and thanks for coming for this talk. So, without much further ado, I am not here to change your mind about what serial you have. This is just going to be a use case for understanding AI explainability. So, let's get started. What can you expect to take away from this talk is a basic introduction to explainability, keeping in mind that all of you are coming from different backgrounds, and different expertise levels. So, a basic introduction, then how are explainability and interpretability different? And I've written a small piece of code, a linear regression model, to show how sharp values and line values can help you understand that how features are affecting the model prediction. This is about myself, and feel free to connect on LinkedIn and Twitter. My PhD specialization is in data privacy, but ethical AM and AI and MLOps is something that I'm working on now. So you have ML models working everywhere behind recommenders, even behind games. And while some of you would be involved in development, some of you might be handling the business side. So we know that ML models, they are opaque. They are notorious for that. They're very different from conventional software in that sense. So how is this opacity hurting the stakeholders involved? So first of all, if I'm talking about stakeholders, if you take the example of a model that's working for maybe a loan credibility score, so a model would predict that whether the particular person, they should be allowed to take out a loan or not. This is their score. This is the confidence that they should be allowed to take out the loan. And this model, it would be used by a manager sitting in a bank. It would also be used by a scientist just to test out what they have devised. So a certain level of results, they make sense to the data scientist, but where a loan manager is sitting, they have different set of expectations. They would want to know that, okay, what were the factors that made one person undesirable for a loan and the other not? So there might also be some defective correlations between the features in the data set, and definitely difficulty in debugging, because any one of us who has developed an ML model have been through that pain, that it is very difficult to debug sometimes. That okay, on paper the data felt good, it was intuitive, it should have worked, but why? Okay, I'm also getting a good accuracy, but then what about a certain score, F1 score of what about recall? Why am I getting so many problems? Why is my prediction not working fine in production? It was working fine in the training. So all these list of debugging help that happens through explainability. Then loss of control. So you have an opaque model at hand. Some of the inner workings of the model, they need to be understood to control any side effects that might happen in production. So to keep a watch on that, also you can use explanations. For instance, you might also be like some feature might have crept in while doing the modeling. You didn't notice it, and it started to make impact on the model predictions. Again, it would spiral into a loss of control over the performance of the model. Then bias. Bias is again a very big concern when we're talking about modeling, especially if we want to see a certain feature which is not working, which is working, starts to work against or in favor of a certain demography. So explanations would also help you with that. All these, they're like lot of words, but when we see the code, maybe then it would get more clearer. Definitely, serial data set wouldn't have anything to do with bias. So, a major diversion may also happen between the model performance and the vision, the business vision, or the research problem that you started out with. So, keeping an eye on the model performance in view of the feature attribution helps in making your ML model less opaque. It is no longer a black box now. So practical explainable AI solutions should focus on different stakeholders, as I had said earlier, whether you are developing it, whether you are using it, whether you are making business decisions based on it. You need to be aware of the dynamics that are happening behind the predictions or the classifications. So again, this slide, it has a lot of information. Let's just focus on the right part first. So what do explanations look like? On the right side, we have the explanations for a VGG16 model. Some of you might be working with computer vision. So there are images there. They might have different color channels. They might have a lot of happening in them. They might be very noisy or they might be blurred. But somehow our computer vision models, they are so smart. They know like, okay, if this is a chihuahua and this is a cat. So how does that happen? And whether this is a stop sign when you are training a model for an only auto driving car. So how does that happen? The explanations that we generate, they look like these heat maps that we can see. The blue and the followed by light blue and yellow parts. These are highlighting the very important features of each image, which tell the model that, okay, focus on this area and this is the part of the image that is helping me decide whether that's a park bench, whether that's a street sign, a stop sign, or whether that's a chihuahua. This also reminds me of that funny meme where we have muffins and chihuahua. So again, you can see why it happens, because if you see the middle image of the chihuahua, if it were a muffin, it would be very easy to confuse the model. On the left side, I have a textual form of the explanation. So, how does it look if we are generating an explanation report and a model which is classifying vegetables? You might have a potato, you might have a broccoli, and you might have lemon. So, the output would be like this is an image of a broccoli. That is the label, the output of the model, and the text in orange is the explanation. So this is the reason why the model said that this particular vegetable, it's a broccoli, because it is green, has a flowering head, and a thick stem with small leaves. So it is backing the output saying it's a broccoli by these justifications. So coming to how explainability and interpretability are different, where we talk about explainability, it is seeking to give a human understandable form, whereas interpretability works more on the model level. So, what you can do, you can see the change in the output for specific changes in the input. For instance, let's take this example where a trained model would decide whether the human kid would like a particular food item or not. And what are the food items they have been given? We have French fries and we have given them broccoli. It's common sense, but okay, there are some kids who like broccoli. So let's just say this is what we taught the model, that it was given one input set x1, which said that the underlying potato that was used was a underlying vegetable was a potato. It was fried and the spiciness was low, and human kid was happy. Then second instance was the vegetable was broccoli. It was steamed and the spiciness was low, which gave us a sad kid. So the model was trained this way on a large data set, training data set. Now, how would interpretability would help you? So let's say we want to continue with broccoli itself, but how do we make the human kid happy? So the model took the vegetable, the cooking method, and the spiciness. Low spiciness is the constant. So let's see, if we do a cooking method, we change it to fried. So a fried broccoli with low spiciness, it would be predicted as a happy emotion based on how the model was making decisions. The model had been trained and it is using this input set and checking, okay, how do we change the output, which is the emotion of the kid. So these were all about what I have to talk about, the introductions. Let's go through the code. Is my screen visible? Yes. So it's a very
Yes, please.
simple,
Yes.
okay, thank you. So it's a very simple linear regression model that I trained on serial ratings data set that I originally took from kaggle.com. So I can also share the link to this collab notebook later on after the end of the talk. So you can change the things around this, and the data set is hosted on GitHub, my GitHub. So it's all available for your use. So what is the data set about? There's the name of the serial, The manufacturer. So we have certain manufacturers associated with the cereals. This type was cold or hot cereals. These are specific to the US, these cereals. The data set is specific to that. Then the calories per serving for the cereal, the protein in grams, fat in grams, and other ingredients that we see on the boxes of our cereals. And sometimes it's already there. Other important features were the weight that's there in one serving, and it's in ounces, and the serving. The cups is like again a number of cups in one serving, and your output is the rating that people had given. So it could also be an average of the survey that was taken. So these are the ratings given to each of the cereals. So I just checked who were the manufacturers. They also needed to be changed to numbers, and there were some garbage values like -1, which I changed to a 0. So I was curious about what's the factor, like how is a manufacturer changing things, but I let it be for this run. Maybe when you get your hands on the notebook, you can remove that and try the code again. So this is the distribution of the ratings. So apparently, average rating was the most reported value for the target, and okay, people are not too happy about cereals. So a rating of 90 is very less. I think only 1% reported that. So I changed all the strings to numbers. Type is 011. I let cold and hot cereal types remain because that's fine. There were only four hot types, others were cold, the manufacturers. And we would not be using the name. So I removed the name because I didn't want to consider name as one of the features for the model. So this is where we declare the model, linear regression model, we train it, and we make predictions. So this is a very lazy piece of code. It is very basic linear regression model. And somehow we got a very good performance from it. So not bad. And okay, this is a linear regression model, and you must be aware that we have coefficients associated with each of the features. So why do we need to make things complicated? Why do we need explanation anyways? We have these coefficients. They have the direction as well, the negative ones and the positive ones, how they influence the prediction. So why we need the explanations? So coefficients are fine, but if we take the weight feature, as I had mentioned earlier, the weight had been provided in ounces. So right now the coefficient is -0.04. Now what happens if we move to another country, we try the serious data set for another country, they have the metrics system which wants to measure the weight in grams. So 1 ounce is 28.35 grams. So how would the coefficient be modified then? It would be divided by 28.35, and our new regression coefficient for weight would be this. Now this is a very small value, but this should not mean that, okay, there's a typo here. But this should not mean that weight was not important. Okay, this was another example I wanted to put. Or if we take another example, for instance, it was a housing data set, housing price data set, and each age was given in years, and it would have some regression coefficient attached to it. Now, if we change the data set to the daily measurements instead of yearly, we go to the daily granularity. Then again, the coefficient would change. We would divide it by 365 because 365 days are there in 1 year. So again, the coefficient would differ, but that should not mean that the importance of the feature is changing with respect to model performance. So let's get started with the explanations. SHAP is based on Shapley values, and it works on global level. So if we consider the whole data set, SHAP scores would tell the importance of features with respect to the whole data set, the model performance. So the concept behind sharp values is that it's based on game theory. And just like in game theory, a player can join in and they could leave. We could have just one player at a time or 100. So the performance of a game and how it's going to progress, a certain player would have uh, they would be contributing to the game on their own individual level, and we have the game on the whole. So similarly, we have a model performing on the whole, and your features are the players that are joining in and leaving. And we see how the model is performing with each of the features' importance when they're taken away and when they're added. Another example that was given in the Google AI explainability white paper, it was about a firm which had three employees, A, B, C. And okay, it was time for appraisal, and the company had certain revenue that it had gained in the past year, and ABC had joined like a couple of days apart. So this time of appraisal it had to decide that who had contributed best to the revenue. So a Shapley model can be constructed in this way, that what was the revenue gain when only A was there, when only B was there, and when only C were there. Like A was there, B and C were not there. B was there, A and C were not there. C was there, and A and B were not there. So what were their contributions to the company revenue? So on similar lines, we develop sharp scores for the features. So these are the partial dependence plots that are very typical to sharp values. And here I'm considering calories first, sugars. You can plot dependence plots for each of the features. So the direction of the plot, it is decided by in what direction the feature is impacting the performance. So this is some helpful text that I had put in for your reference. So this line is the expected model value, okay, the overall value. And this is the average value of the median for the fiber percentage, because I plotted the partial dependence for the fiber feature. In this case, the horizontal line is for the sugar values, sugar feature. So this is your dependence plot. Here we can see that it's a linear relationship. In some data sets, this might not be a linear relationship. It could be a very volatile graph as well. So this intersection is the part where we calculate the sharp score. But let's get to this when we see the waterfall plot of the sharp scores. So this is what you usually see on systems that are giving you sharp scores for the features and how they are attributing to the model performance. So if you just turn your head to the right, it would look like a histogram. But the thing is, we have directions attached to this. So colors are not intuitive, but red means that the attribution is positive, that it is adding to the model output, while the negative ones, they are not adding to the model output. And there's an sharp score is the magnitude to which they are not adding to it. So we have a model output that we start with. For all the red features, they are adding to it, the model output, while the blue ones, they are decreasing it. So we are just going towards the final model output. In this case, 64.82, it was the average rating. And these were the values of each feature and how they had contributed to the prediction of value 64.482. Over here, I've written 14 because there are 14 features here. So this was about global explainability, where we are talking about the whole data set, the whole table, including all rows. Lime is used for local explainability when you would like to focus on a specific row. So again, this piece of code is there, a train and explainer. So let's take a average value, like average rating value. So this is just one instance where the rating was 58.3. It is somewhat average rating for a cereal. And this is where lime, again, it's like a waterfall, you can see. In this case, sodium, calories, vitamins, they played an important role. While overall, when we talked about global one, Carbs and sugars played a very important role, followed by sodium. And fiber, somehow it was not helping the ratings. So for an average rating, these would be the feature values for one, if you consider it as a single row in a data set. For a rating 58.3, we are just focused on that one row where the feature values were these and these were their attributions. Now let's come to a lower rating of 37.06. Again, this is just one row of the data set where the rating was not so good. So these are the feature values for the case when the rating was not so good. So these are very specific instances of the data set. And sometimes they also help in pinpointing bad performing rows of where the output was not good, why it was not good. These were your feature values. Maybe you can check against them. So again, we have the attributions for this very rating. Carbs had a very positive impact. Calories did not. Maybe vitamins were there, so maybe the person who gave the rating, they were a bit lenient with giving the rating. Maybe they wouldn't have even given 37 if it were not for the vitamins. Then I took another random one where I'm again, it's a random row which I picked, 53.32, and these are the feature values. So I was also curious that what if the cereals, they had their names with them. So what if there was a fruit component in them? Then how would the explanations change? So I just made another column with fruit, and they were like strawberry flavored ones and with fruit bits ones. So all these cereals I marked as one and the others as zero for the absence of any fruit component. I again trained a linear model on it, linear regression model. Okay, this is absolutely fishy, but again, we are concerned more with explanations and we can see how we can get a better model performance later on. So now we have another feature, fruit. Okay, regression says that okay, it doesn't have any impact on the model output, on the predictions. Whether your cereal has a fruit component or not, it's okay. It's not affecting the ratings. But can we believe that? Let's see. Let's look at the explanations. So again, I plotted the partial dependency plots. Let's go to the waterfall to give a better picture. As you can see, the sharp score for fruit is 0. So it means that whether the cereal had a fruit component in it, maybe raisins or maybe dried strawberries or apples, it didn't have much effect on the rating that people gave to the cereal. So it is more to do with carbs, which are directly associated with the base of cereals, whether it's oat based or rice based or wheat based. Carbs are definitely there. Sugar is an important factor. So people probably prefer sweeter cereals. They rate them higher. Like, okay, we like this cereal more because it is sweeter. Sodium again is a taste component. So sugars and sodium, they are there with a very major positive impact on the ratings. Fiber, not so much. This might be due to the fact that oat-based cereals, they are not that popular, as per my understanding. And rest values, vitamins, fat, they have some effect on that, but not fruit components. So you can check this notebook. I also implemented one explanation for the fruit case as well. So again, it is reiterating the fact that fruit components do not have much effect on the ratings. And let me just share the link to this notebook on the chat. So feel free to make a copy of it and make changes to it. It would be great. And please get back to me if you see any mistakes or if I should have considered other features as well. So can I send it to the studio chat? I'll just send it to
Uh,
the studio chat and maybe they can forward it.
yes, Gatha. I think what we could do is to actually share it on Discord as well. That way,
Yes, sure.
everyone can
So
access to it.
this
I,
is all
I can
I had
help
to
you do that.
present today, and yeah, Sure. Thank you, John. So this is from my side. I have shared the link on the studio chat as well if you would like to forward, and definitely on Discord as well. So please questions.
Great. Thank you so much, Gatha, for your time. It was excellent. I was very curious about how Lime and Shap compares in terms of explainability. So that's a good overview of it. I so the audience, those who are listening to this talk, feel free to post your questions in chat, in the YouTube chat. I'll be monitoring them, and I can field any questions to Gatha if necessary. Well, while we're waiting, I have a question of my own, Gatha, if you don't mind me asking. I saw in your last analysis when you compared the SHAP results and the Lime results, uh, if I recall correctly, the carbs was one of the high contributing factors for the selection, but in SHAP, but for Lime, I didn't see that it was showing up. Could you like give some explanation for that?
This is for the carbs. Okay, this is for a particular row that a poor rating. If I'm taking 37 as a poor rating, these are the values of the feature that were available for that particular row. So carbs were in grams. So it had very low value of very less grams of carbs, but the its impact on the model output, the prediction was high. It was towards the positive side where this would score.
Actually, I think I was referring to the last example that you had, where you introduced fruit as the additional columns,
Okay,
and when you compared
okay.
the results,
Uh,
yeah.
yeah. In fact, it was pretty much the same as earlier. What I was trying to communicate was that fruit components, they didn't play much role in the ratings. I had
All right,
hypothesized, and this is what I wanted to test, that what makes a cereal popular? That maybe the raisin ones, or the ones, maybe Apple Jacks. It's so popular, but is it because of the apple flavor, or the raisin brand ones? Is it because
yeah,
they have raisins? So we cannot say that okay, adding raisins would as such give us a good rating, but definitely people are going for taste. If you see sugars and the sodiums, they were ranking high and they are contributing to the ratings. So we can maybe a cereal which is nice in taste, which has a good texture. So
okay.
that texture because of carbs. So maybe then it would get a good rating.
Okay, 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 interesting. All right, there are two questions from chat, and I'll just um, post them up here. So the first question is by Zeno. Great
Okay.
talk. Thanks. You are mentioning computer vision analysis. I don't see them in an analysis. Could you give some insight into that?
Yes, I did not take that example because I wanted to use a very simple model, and that's why I did a linear regression model. But thanks for suggesting this. Maybe I'll try something and post it on my Medium. I write on Medium as well, so make a post
Hmm.
there. But
Excellent. Yeah, I think that would be
explainability
good.
is definitely it's a good use case for computer vision as well, especially if we are talking about medical images, and if you're talking about X-rays or retinal images, you would definitely know more. But even in retinal images, there are certain components, there are veins that need to be considered for whether that person is diabetic or not. So computer vision is definitely a very good use case for explainability.
Great. Excellent. Thanks for that. There's a second question by CryptoPie. I will post it up here. CryptoPie asks, can Snap be used to I assume that's SHAP. SHAP be used to evaluate
Yeah, yes.
RL or deep RL models?
I've not used it yet. I've just used it on simple ML models. But if we have an internal state associated with learning, uh, I wouldn't give some answer out of the hand because I've not tried it.